Hey everyone, and welcome to this explainer. Today we are grabbing our virtual hard hats and stepping into the role of the analytical excavator. We're going to dig deep, and I mean really deep, into some core Cambridge physics concepts, specifically from the 0625 syllabus. We're going to start our excavation at the macro level, looking at the heavy lifting concepts of work and energy, and then we're going to dig all the way down into the microscopic world of thermal effects and particle motion. This is all about taking these foundational physics principles and laying them out clearly, step by step, so you can absolutely lock them into your memory for exam day. But before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's dive into this. Here is our revision checklist and our map for today's excavation. Section 1, digging into work. Section 2, interpreting Sankey diagrams. Section 3, potential to kinetic energy. Section 4, the kinetic theory model. And finally, Section 5, thermometer deep dive. All right, Section 1, digging into work, the surface layer. Now, you might be wondering, what exactly is work in physics? Because, in everyday language, you might say you're doing work when you're just sitting at a desk writing a long essay, or maybe you're outside digging in the garden. But to scientists and engineers, work has a very strict, highly precise meaning. Work is only done whenever a force actually makes something move. If there's no movement, well then literally no work is done in the physics sense, no matter how physically exhausted you might feel. It's kind of crazy, right? The standard unit we use to measure this is the joule, represented by a capital J. So the absolute crucial point you need to remember is this. Exactly 1 joule of work is done when a force of 1 Newton moves an object exactly 1 meter in the direction of that force.
So, to make this quantifiable, we use a beautifully simple word equation. Work done equals force multiplied by distance moved, or if you prefer the symbols, W equals F times D. But listen closely, because there is a vital condition attached to this formula that examiners absolutely love to test you on. That distance moved, it must be in the exact direction of the applied force. For example, if you're pushing a heavy box horizontally across a floor, you only count the horizontal distance the box traveled. It makes sense when you think about it. The greater the force you apply and the greater the distance you manage to move it, the more work you've ultimately done.
Let's turn this from passive listening into active problem solving, all right? Question for you. How much work is done if a force of 12 newtons moves an object a distance of 5 meters? Just think back to our formula. W equals F times D. We take our force, which is 12 newtons, we multiply it by our distance of 5 meters, and boom, we get 60 joules of work done. It really is that straightforward when you apply the framework correctly. Moving on to Section 2, interpreting Sankey diagrams, the fossil record. Now, what's really interesting about this next concept is that when energy transfers from one store to another, it almost never does so with 100% efficiency. Some of it always escapes. It's just a fact of life. To solve this complex problem, engineers use Sankey diagrams to elegantly map out exactly where the energy in a system is going. It perfectly visualizes a massive rule in physics, the conservation of energy. Whatever goes in at the start of the arrow simply must equal all the little bits coming out at the end. Let's extract the core trends you really need to know here. The defining feature of a Sankey diagram is that the thickness, or the width, of the arrows represents the exact amount of energy. So a thick arrow, that means a lot of energy. A thin one means just a little. Usually, the straight arrow continuing forward represents the useful energy, the stuff we actually want. The downward curved arrows, on the other hand, represent wasted energy. And this most often takes the form of thermal energy spreading out into the surroundings. Honestly, it's like the inescapable tax of the universe. Energy naturally spreads out as wasted heat, making it less and less useful to us. But remember, if you were to add up the thickness of that useful arrow and all the wasted arrows, it will perfectly match the thickness of the initial input arrow. Every single time. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, Section 3, potential to kinetic, visualizing the drop. Okay, let's picture this. Imagine a heavy brick in free fall. Before it even begins to fall, it possesses a certain amount of energy merely because of its height and the Earth's gravitational pull. We call this gravitational potential energy. In this specific example, let's say the brick holds 20 joules of it in its store. But as it falls toward the ground, it loses that height and, naturally, it speeds up. What we're witnessing here is a direct, one-to-one relationship between the work done by the downward force of gravity and the energy being transferred into actual motion. Let's move through this and see how it builds chronologically throughout the drop. In step 1, before the drop even begins, the brick is at its highest point, so it has its absolute maximum gravitational potential energy. Step 2, as it falls exactly halfway down, it has lost exactly half of that height, which means, you guessed it, it has lost half of its potential energy. But remember our law of conservation, that energy didn't just vanish into thin air, it transformed directly into kinetic energy. So, at that halfway mark, the energy is perfectly split. Finally, in step 3, right at the fraction of a second before hitting the ground, the height is 0. All of that initial potential energy has now been completely transformed into its maximum kinetic energy. Those 20 joules have been fully 100% converted into speed. Section 4, the microscopic dig, kinetic theory. Now we're digging deep into the microscopic world. The kinetic theory is a model scientists use to explain exactly how solids, liquids, and gases behave. Scanning the data, the core trend is super clear. In a solid, the particles attract each other so strongly that they are practically locked in place. They just vibrate about fixed positions, and that's what gives solids their fixed shape and volume. In a liquid, those attractions are a bit weaker. The particles still vibrate, sure, but they can actually slide past one another and change positions. That's why a liquid has a fixed volume but can flow to take the exact shape of its container. Finally, in a gas, the attractions are extremely weak, almost non-existent. The particles move about completely freely and randomly at very high speeds, resulting in no fixed shape and no fixed volume whatsoever. So the behavior of the material is entirely dictated by the strength of attraction between its tiny particles. All right, this brings us to a super important, highly tested definition: internal energy. When we talk about internal energy, we're referring to the total combined kinetic and potential energies of all the atoms or molecules inside a material. Now, it's absolutely vital to clarify the difference between heat and internal energy here because they often get mixed up. The hotter a material gets, the faster its microscopic particles zip around and vibrate. Because they're moving faster, they have more kinetic energy, and therefore, the material as a whole possesses a higher internal energy. When a hot material touches a cold one, that internal energy is transferred, and that active transfer is what we formally call heat. And finally, Section 5, Thermometer Deep Dive, Measuring Energy. You're probably familiar with traditional glass thermometers, where a liquid expands, right? But modern engineering relies heavily on electrical thermometers. Two key ones from your syllabus are the thermistor and the thermocouple. Let's break them down. A thermistor relies on a component that actually becomes a much better electrical conductor as it gets hotter. So, as the temperature rises, more current flows from its battery, giving you a higher reading. A thermocouple, on the other hand, is quite clever. It uses two different types of metal joined together at two junctions. When there's a temperature difference between those two junctions, it almost magically creates a tiny electrical voltage which drives a current. The bigger the temperature gap, the bigger the current. What you really must take away from this is that every single thermometer in the world depends on finding a specific material property, like volume or electrical resistance, that varies predictably with temperature. As we look at all this thermal energy, I want to highlight the specific quote from the source material. Thermal energy is the energy of randomly moving particles. It has a natural tendency to spread out. As it spreads, it becomes less and less useful. And this brilliantly illustrates the ultimate, massive challenge in physics and engineering. When you burn fuel in a power station, you get a highly concentrated source of heat to boil water and spin a turbine. But as that heat inevitably escapes and warms up the surrounding air or cooling water by just a few degrees, you can't use it to do work anymore. It's just too spread out. This overarching theme of energy dissipation is exactly why engineers spend their entire careers striving to make power stations and engines as efficient as physically possible. So, to wrap things up, I want to end our explainer today with a pretty provocative question. If most renewable energy sources, like wind or solar, have absolutely no fuel costs, why isn't the electricity they supply free? Well, think about the immense work done just to build the massive infrastructure. Think about the wasted thermal energy as the electricity travels for miles and miles through the grid. Applying these core physics concepts to real-world infrastructure is exactly what takes you from just knowing the facts to truly mastering the subject. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. AC Exams, your Cambridge success starts here.